Welcome, friends, to my second lecture on the Pigeonhole Principle. I hope you enjoyed the first lecture. I hope you looked at some of the problems again. The key to doing problem solving in mathematics is actually to hit the pause button right after the problem is stated. Try it yourself, and if you don't succeed, or even if you do, compare your answer or your thoughts with what happens. This is actually the correct way of doing problem solving. It's not a great idea to look at the problem and immediately look at the solution and go on from there, because then it's not a learning experience. Let me quickly revise what the Pigeonhole Principle says. Luckily for me, that's not going to take very long, and for you, therefore, to revise. And let me begin that way so that then I can go on full steam into the second set of harder problems on the Pigeonhole Principle, or let's just say different problems. So the pigeonhole problem essentially consists of making pigeonholes or letter boxes. The symbol I used for the letter boxes was M, so there are M pigeonholes or M letter boxes. And the number of letters that go in there is N. These N letters go into these letter boxes. And I'm going to assume that N is greater than some K times M. K is a fixed positive integer. Conclusion: there exists a letter box containing more than K letters. More than K letters. At least K plus 1 letters. This is actually the generalized version of it, but really there's not much between the generalized version and the regular version. The regular version would be the case where K is equal to 1. So if the number of letters is greater than the number of letter boxes, there'll be at least one letter box containing more than one letter. This is the Pigeonhole Principle. All right. Now, let me go on and look at a varied set of problems that have to do with the Pigeonhole Principle. I'm going to begin with a problem which is not quite geometric, but not as arithmetic as many others. It has to do with chess. I hope that you know how to play chess, but if you do not, I will tell you the basics that are required to solve this problem. All right, let me first read the problem, and then I will tell you what I require from it. So there are 33 rooks. A rook is a chess piece. I will tell you more about it in my next slide, but let me just go on. These are placed on an 8x8 chessboard. Actually, chessboards are typically squares, and each side of the square is 8 units, and they're alternately black and white. And the reason we mention this 8x8 chessboard is because in problems that deal with counting or parity or combinatorics in general, we often deal with a hypothetical non-square M cross N rectangular quote-unquote chessboard. It's not a real chessboard, but for the purpose of argument, many of the arguments are made in a hypothetical situation where we assume that we have a rectangular shaped board which has M cross N squares or M into N squares. Anyway, right now I'm dealing with a regular chessboard. It's an 8x8 square, alternately black and white, which is not terribly significant. What you have to do is remember that you've picked 33 of these particular chessmen called rooks, and you have to prove that you can always pick 5 of these rooks which are non-attacking each other. So of these 33 randomly chosen rooks that are to be placed in this 8x8 chessboard, which means you're filling up a little bit more than half the squares, the 32 squares which would be half the chessboard. This is one more than that. You might already be thinking, well, this is ripe for pigeonhole. 33 is 1 more than 32, but well, this will lead you the wrong way. That is not the hint. The hint will really come from the next step. The next step says, prove that you can choose 5 of these 33 that are non-attacking. So before I go further ahead into solving the problem, I must understand what the problem is. What do I need to do to understand this problem? I guess I need to explain to you a little bit about the rudiments of one particular chess man. This is not drawn to scale. I'm assuming this is an 8 by 8 piece, 8 by 8 square. And there is a chess man called a rook. It is also sometimes called a castle. My ability to draw pictures are not very good, so I will not attempt to tell you what a rook looks like. If you know what a castle means, then you probably can figure out what a rook looks like. All right. That said, let me assume that I've got 8 columns and 8 rows. 1, 2, 3, 4, 5, 6. And so this one is a little fatter. That's 8. And I need 8 rows. 3, 4, 5, 7. So let me just stretch this like this. I hope I have 8 rows and 8 columns. Now, let me just denote a rook by a symbol R. This is how the rook moves on a chessboard. It moves in a direction which is called east and west, or moves along the row it is placed in, or it moves in the direction of north and south, which means it moves in the column it is placed in. It can move any number of squares so long as it does not leave the board. Now, although this does not matter, there's a fixed number of rooks that are placed in a chess game. But since you're not playing the game of chess, we can place any number of rooks we wish. The problem says, and let me put this problem one more time in front of you very quickly. It says that I have this 8 cross 8 chessboard. I have to place 33 rooks. That's a whole lot of them. More than half the squares are filled by them. And no matter how you place these 33 rooks, you will be able to pick 5 of them which are not attacking each other. Now, I didn't tell you what attacking means, but it kind of explains itself given the movement of the rooks. So here are my rooks. So 2 rooks which are in the same row or in the same column kind of attack each other. They kind of come in each other's way and they kill each other. So when you say 2 rooks are not attacking, let's say R1 and R2, they are non-attacking. Non-attacking. It means simply that they are placed in different or distinct rows and also in distinct or in different columns. That definition emerges from the way a rook moves on a chessboard. So plainly put, because the rook moves up and down or left and right, it will kill everything in its path. So if there are 2 rooks in the same column or in the same row, they will attack each other. Now, the problem simply says, place 33 rooks, fill up a little bit more than half this board, any which way you wish, and you will necessarily find 5 rooks in a manner such that no 2 of them attack each other, mutually non-attacking. So how do I attack this problem? What do I have to do? I have to ultimately get 5 objects in the same box. These 5 objects in the same box have to have a property. And that property has to be that all these objects in the same box are non-attacking rooks. All right. For them to be non-attacking rooks, I have to have a formation which kind of defines my boxes, so that when I place my rooks in these boxes, what emerges from the pigeonhole principle is simply that there are 5 rooks somehow in some box. Now, what kind of relation should 5 have with the 33 that is there? How am I thinking of this? Well, what I'm basically thinking of is, in some sense, getting 8 letterboxes. Why 8? Well, if you divide 33 by 8, you get 4 and a bit. If you divide 32 by 8, you get 4. And so if you had 32 objects and you place this in 8 letterboxes, it is feasible, it is possible that each letterbox gets 4 objects each. But the moment you have one more than 32, pigeonhole principle or its generalization will tell you that 2 of these objects, 2 of these letters, or sorry, 1 more than 4 of these will go into the same box. And 1 more than 4 is 5. Little convoluted thinking, but pigeonhole principle working backwards is always a little tricky. So this is what I'm planning to do. I'm planning to devise a scheme in which I have 8 letterboxes, 1, 2, 3, and I'm going to be lazy and not write all the numbers, 8 letterboxes. I have to place 33 rooks in there. And the pigeonhole principle says, because 33 is more than, it's 4 times 8, that's 4 times 8, not 4.8, plus 1. 33 is more than 4 times 8. Pigeonhole principle will tell me what I require. I will require the fact that, or conclude the fact that more than 4 of these rooks get into the same box. And that's 5, and that's what I'm looking for. So the strategy is straightforward. Devise a scheme in which you have 8 letterboxes. So a subset consisting of 8 classes. Each of the class has the following property, that any 2 rooks in the same class do not attack each other. So somehow, since we have no idea where these 33 rooks are going to be placed within these squares, you have to break up all the 64 squares in a chess board into 8 classes in a manner such that 2 objects go into the same class precisely when those 2 objects, considered as rooks, do not attack each other. This is what one is thinking of. All right. That said, I have this scheme prepared. I don't have squares to enclose this particular array. I hope you can see it. I made use of the sheet that is given to me, which had lattices. I used the corners last time in my lecture 1 for lattice points. Now I'm going to use the inside of the squares. There are 64 squares in there. They're not colored. It is not significant that they should be. But what is important is the formation of the numbers. There's a certain pattern to which the numbers are, in which the numbers are written. You can see the pattern. In the first row, I've got the numbers 1 through 8. In the second row, the 8 comes to the beginning of the array, and every other number gets shifted by 1 unit, and this keeps going. So I end with the last row, which begins with 2 and goes in an increasing fashion until I cyclically complete that particular sequence. All right. What is the significance of these numbers? First and foremost, you'd have noticed that I've got numbers 1 through 8. What one is trying to do is place the numbers, the same numbers, or the squares occupying the same numbers in the same box. You will recall from the previous slide, something like this, that I had 8 boxes, and the idea was to place the rooks in those boxes. Now, I'm not going to be done placing the 33 rooks because I have no idea where those rooks are. So I really have to have a scheme where I allot by a certain scheme where to attach each of the squares, the 64 squares, into these boxes. And that is the scheme that I just wrote up. So wherever you see a square marked 1, put that square in box 1. Wherever you see the square marked 2, put that in the box marked 2. You will find that each of the 64 squares is labeled exactly one of the numbers 1 through 8. Therefore, this scheme will attach or allocate to each square exactly one number, and that is the number allocated to each square. Now let's look more closely at why one could have thought of this allocation. Look, for instance, at the squares occupying or labeled number 1. There's an unmistakable geometric pattern to that sequence. You might notice, although this is a little bit small, I think, on the screen, that they occupy the diagonal 1, the main diagonal. 1 is on the main diagonal. So what we propose to do basically is look at all the squares in the main diagonal, put them in box 1. Remember now the conclusion that I wish to draw from doing this. The pigeonhole principle is supposed to say something to the effect that when I pick any 5 letters, then two of them must, when I pick any 33 rooks or letters and place them in the pigeonholes, some 5 of them must be from the same letter. Now imagine the situation that those 5 came from box number 1, which basically means that that box number 1, which has the possibility of having as many as 8 numbers out there, because exactly 8 of the squares are numbered 1, are the placements of the rooks. It signifies, if pigeonhole is to apply to box number 1, that I've placed those 5 rooks in 5 of those 8 slots earmarked for the main diagonal. Now, the way the rooks are placed, these rooks are going to be non-attacking because no two of them are in the same row or the same column. If you attach a pair to each square, its row number and its column number, then each pair of rooks will have a distinct row number and a distinct column number. This is the meaning of saying that they are non-attacking. So all that one has done is looked at the top left corner, 1, and picked 7 more so that they are mutually non-attacking. Could I have picked any more square and labeled it 1? In fact, by pigeonhole principle, no. Because the moment I picked a 9th square beyond this 8, I would have to repeat one of the rows because there are only 8 rows out here. As a matter of fact, by the same logic, I would have to repeat one of the columns. The moment I place 2 rooks in the same row or in the same column, they are no longer mutually non-attacking. So therefore, it is not possible for me to pick more than 8 squares with the same label, because the moment I pick more than 8 squares with the same label, I must have, by pigeonhole principle, the fact that 2 of them are attacking. And if my conclusion is to be non-attacking, I have no choice in the matter. So whatever scheme I devise, it must have exactly 8 squares earmarked 1 and exactly 8 earmarked 2, and so on and so forth, all the way till 8. It's a very tight fit. So this is one scheme in which, for example, once I decide to permute the symbols 1 through 8 in a manner such that 1 occupies those squares, 1, 1, 2, 2, 3, 3, and so on and so forth, and then I focus on 2. Notice that 2 is also along a diagonal, not the main one, the one next to the main one. And then there is a little bit of a leftover, and then you decide where you want to put that. Once it's an off main diagonal, it's occupied 7 of the squares, there's only 1 square left, it decides itself because there's only 1 free column and only 1 free row. Anyways, you can decide by a certain scheme how you can place these numbers. This is not the unique way of doing it. There could be other ways of doing this. Now, once this has been placed, what is going to happen is I'm going to place, therefore, 33 of my rooks occupying 33 of these squares, of these 64 squares. These 33 rooks are going to sit in box numbers 1 through 8. So by the pigeonhole principle, because there are 8 boxes and there are 33 pigeons or letters to place them in, there will be some box number or some squared number which contains 5 of these rooks. That's because 33 is more than 4 times 8, as I mentioned right at the beginning. So now the moment you have 5 of the rooks occupying the same numbered square, for example, numbered 1 or numbered 3 for all that I care, automatically the problem is solved. It is solved because that is how the setup of the squared numbers was. We designed the labeling of the boxes in a manner so that the net result came out to be that any two numbers, any two rooks in the same numbered square are non-attacking. And so this is actually a back calculation. You want the pigeonhole to work, therefore you have to connect 5 to be one more than something, and that something therefore has to be 4. That is one end of it. The other end, which is even more important is and more significant, is the net conclusion. The conclusion is that when you have 2 in the same box, what should it signify? It should signify that they don't attack each other. Therefore, what property must the objects in the box have? They must have the property that 2 objects go into the same box precisely if they are non-attacking. Now, there is room here for maneuverment. It could have been for maneuvering. It could have been the case that you have also 2 rooks in 2 different boxes that do not attack each other. That does not take away from this logic. But unfortunately, there is no ground to do that. There's no space to do that, as I just argued. So in fact, there is no option but to place exactly 8 in each of these different labels. Anyway, so that is the end of this problem. It's a little different. It's a little game-oriented, not very geometric, but there's a picture there to draw. So I thought I'll begin with this. My second problem, while I'm on chess, uses chess, but only slightly. You actually do not need to know how to play chess to do this problem. It involves a chess player. This is a chess player who is a serious chess player. He is actually preparing for a match, for a tournament. He needs to be in top shape. He has a little bit of time left to prepare before the tournament. He has, and these numbers are cooked up so that things work out, 77 days to prepare for a tournament. He needs to be in shape, so he needs to play at least 1 game every day. That is condition number 1. At the same time, he doesn't want to tire himself out, and therefore he decides that he will not play more than 132 games over the entire period of 77 days before or leading up to the tournament. So again, the restrictions are that he has 77 days of preparation. On each day of the preparation, he plays at least 1 game. On the other hand, at the end of 77 days, he should have played no more than 132 games. No more than. What you have to prove is that there is a consecutive sequence of days, for example, from day 13 to day 25, over which he plays exactly 21 games. So there's a consecutive sequence of days over which he plays exactly 21 games. Now, naturally, that sequence of days cannot be any more than 21 days because on each day he plays at least 1 game. So if you were to take a consecutive stretch of, say, 22 days, you would have played at least 22 games. What this asks you is a precise sequence. Asks for the existence of a precise sequence of consecutive days over which he plays no more and no less than 21 games. All right. So let that sink in. And while that sinks in, let me just turn this and try to work on this. What do I have in hand? So I have a guy, a player, who has 77 days to prepare. Let's just call A1, A2, A3, and so on and so forth, A77. A sequence of positive integers, which tells you how many games he has played at the end of that day. So A subscript n denotes the number of games he has played at the end of n days. So A1 will tell you how many games he has played after day 1. A2 will tell you how many games he has played after day 2, and so on and so forth. And A77 will tell you that end of my preparation, this is the number of games I have played. Now, what can I say about the sequence of numbers? By definition, you have played at least 1 game at the end of 1 day, Therefore, A1 is a positive integer, and that's all I can say about it. A2 is more than A1 because at the end of day 1 or on day 2, he's played at least one game. And if A2 denotes the number of games played at the end of the second day, A2 is more than A1. This sequence goes on. It's what we would call a monotonically increasing or a strictly increasing sequence of numbers. And I'm going to denote it by putting a few dots at the end of it. And write less than A77. Now, A77 is no more than 132. If you recall, the total number of games that he could have played at most is 132. These are very cooked up numbers. And somewhere down the line, when you apply Pigeonhole Principle, you have to be able to think out of the box, pun intended, and figure out what the connection is between all the numbers that are thrown at you. This is a little daunting out here. This is slightly different from the others. But let's see if you can piece the numbers together. What are the numbers that are given to us? Let me throw this problem again at you. Let me look at it one more time. Well, one number that strikes me right at the beginning is 77. That's somehow significant to the whole problem. Then it says he wants to play at least one game. I will let it pass. It simply means that these numbers are distinct. The next significant number that I see is 132. What is the connection between 77 and 132? I have no clue. I can't see a direct connect between them. It's not like it's one more than a multiple of 77. I need to go on. I need to go on also because I haven't drawn the conclusion. What is the conclusion? So there's a sequence of consecutive days over which he plays exactly 21 games. If you read this problem backwards, then it probably will make the most sense in terms of figuring out how to do this. So this is not dissimilar in a certain sense, or should I say it has some common things with the problem we discussed in lecture 1, the one in which we showed that no matter which n integers you take, there will be a subset of that set of integers which is a multiple of n. I actually did it for n equal to 10, and I hoped you found time to work this out in the general case. Well, this is something similar to that. So the three numbers I take back with me are, and I write it on the sheet, 77 for the total number of days, 132 for the cap on the number of games, and 21 for the number of consecutive days, total number of consecutive games that he must have played, total number of games he should have played over a consecutive period of days. Over a consecutive period of days. What does that mean? Well, supposing that consecutive period of days was between day 1 and day 22. As in, day 1, he has played A1 games. At the end of day 22, he has played A22 games. How many games has he played in between? Well, A22 minus A1. What is the number of games he's played between, say, day 5 and day 63? Well, it's A63 minus A5. So plainly put, AM minus AN denotes the number of games he's played between days or on days n plus 1 all the way up to and including day m. Now, do I know what this difference is? I don't. What do I want this difference to be more significantly? I want this difference to be exactly 21. I want to construct or show the existence of two numbers m and n so that am minus an, which denotes the number of games played in this interim, to be exactly equal to 21. Because that's what I want to conclude. I want to conclude that there's some consecutive days over which he plays exactly 21 games. Well, that's the hint. Let's start with another sequence. Let's start with the sequence A1 plus 21. Now, is that an A something? Well, I wish it was, and I don't know. What is it less than? A2 plus 21. What am I doing? I'm actually adding 21 to all these numbers. So I perhaps can begin with 21 plus 1 and write A3 plus 21 and write dot 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 A77 plus 21. And guess what? I see light at the end of the tunnel. What is 152 plus 21? It is 153. Where's the light? Well, the light is 153 plus 1 is 2 times 77. That somehow should connect. So I've got these two pieces of information. Why did I think of this second sequence? The first sequence explains itself. The first sequence is simply data. I'm just reformulating the problem in terms of what I know in terms of symbols. Why did I think of the second sequence? Because if you look at the second sequence, A1 plus 21, A2 plus 21, etc., 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 I'm hoping that one of those guys in the second sequence equals one of the guys, one of the terms in the first. If that was the case, so if, and there's a big if, this is where the pigeonhole principle comes in, if I could get one of these an plus 21s, which is from the second sequence, to equal one of the terms from the first sequence, then I would get am minus an to be equal to 21. I would get the fact that this chess player has played exactly 21 games on days n1 and n plus 1 through day m on that sequence of m minus n consecutive days. That's what I wanted. And therefore, I am done with solving this problem, provided I could somehow solve the if part. Now, that back calculation is what prompted me to create the second sequence of numbers from the first sequence. All right. Now, I could probably finish this off right here, try to work this out. What can I say about the sequence of 77 numbers between A1 and A77? Well, for starters, they're distinct positive integers. For another, they are between 1 and 132. All right. So I'm going to have this box. This box is going to have numbers 1, 2, 3. And I'm going to, right now, not label the last one. I will leave that for just now. What about the second sequence? The second sequence of terms A1 plus 21, A2 plus 21, I could call them B1 and B2 and so on, that sequence is also a sequence which is strictly increasing, so therefore of distinct terms. They're all positive integers. And they are no more than they're bounded above by 153. So I will now put 153 out here. And I will conclude that all the AIs and all the BIs go into one of those boxes. How many boxes are there? 153. How many numbers are there in all between AIs and BIs? Well, there's 77 of the AIs, so there must be 77 of the BIs, or the AI plus 21s. In all, there's 154 numbers. And if you've come this far, 154 or 2 times 77 is 1 more than 153. It would be too much of a coincidence to think that Pigeonhole isn't going to apply. Pigeonhole must. So the Pigeonhole principle now tells you that 2 of the numbers between the 2 sequences must go into the same box. Is it possible that the 2 of the AIs go into the same box? Clearly not, because the AIs are distinct. Is it possible that 2 of the larger sequences, the BIs, go into the same box? Again, clearly not, because they're also distinct, because the AIs are distinct. What option is left before you? Simply that one of the AIs must equal one of the BIs. Sum AM equals sum AN plus 21. And as happens with all these Pigeonhole principle problems, we work backwards. We ensure that we've figured out how to apply the pigeonhole correctly. Then the final answer is before us. And it now is. It's a happy coincidence that 77 plus 77 is more than 132, 1 more than 132 plus 21. All right. I'm going to move off chess and move into a little bit of geometry and see if there is something that strikes us in this particular set of numbers. The significance of these numbers will probably be clearer to you if you think in terms of geometry, or more specifically in terms of trigonometry. Let me read this problem out first. It's fairly small, does not require much background. Those are always the most dangerous ones because you have not much data to work with. What does it say? It says if you take any 7 real numbers, and although there's no mention whether these 7 are distinct or not, a quick glance at what you want to conclude will tell you that you better take them to be distinct. Because if any 2 are equal, then clearly that the conclusion will be valid. What is the conclusion you seek? Well, you want 2 numbers amongst these 7, which I called x and y, which satisfy this very curious inequality. X minus y over 1 plus xy is between 0 and 1 over square root 3. Well, I'm a little nonplussed about 1 plus square root 3. What is the significance of 1 plus square root 3 in this whole problem? Well, I get the following clue. I see that I have to pick 2 out of 7. So in some sense, I have to therefore have something like 6 letterboxes, 6 being 1 less than 7. If I were to place these 7 real numbers in these 6 boxes by a certain scheme, Pigeonhole principle would tell me that 2 of those numbers would go into the same box. Presumably, these numbers would then take the shape of x and y. And so I should have a scheme where the numbers in the same box are placed in a manner such that that inequality, that very funny looking inequality, a strange looking inequality, because right now we've been typically dealing with whole numbers and we're not used to dealing with real numbers all of a sudden, that inequality is satisfied. How does 6 connect with these numbers? The only numbers I can see there are 0, which is not very significant, and 1 by square root 3. Well, as I told you, let's look a little bit into trigonometry. And let's just very quickly look at a specific function that takes the value 1 by square root 3. This is not drawn to scale, and it doesn't really matter. All I need is a little rough idea of what I'm thinking of. These are lines x equal to minus pi by 2 and x equal to plus pi by 2. And there's a certain trigonometric function, a fairly common trigonometric function that you might have encountered, called tan x. The tan x is actually not defined at x equal to minus pi by 2 or at x equal to plus pi by 2. That's because the cosine function vanishes at those points. The graph of tangent x, you might recall, goes something like this. It passes through the region, and it is in fact a monotonically increasing function. That basically means that any 2 points, x1 and x2, are such that if they are not equal, then x1 less than x2 implies tan of x1 is less than tan of x2. So something like tan x1 is less than tan x2 if whenever x1 is less than x2, and of course I'm assuming that x1, x2 belongs to the interval minus pi by 2 to plus pi by 2. So if I take any 2 points, x1 and x2, let's say x1 less than x2, tan of x1 will be necessarily less than tan of x2. That's the meaning of saying that the tangent function is increasing. There are analytic or other ways of showing that the tangent is an increasing function. It's also one-to-one, and it's onto, none of which I require. All I require now is to use my boxes. I can use the boxes right here. Here is my open interval. The open interval is minus pi by 2 to plus pi by 2. And I'm going to create boxes by subdividing this. I don't know if I can do it very precisely in this picture, but I'm going to try. I'm going to subdivide this interval, whose length, by the way, is pi, into 6 equal pieces. So if I've drawn my pictures correctly, 1, 2, 3, 4, 5, 6, all I will write is 6 equal subintervals. And these are my so-called boxes. So I've got 6 boxes, and what I'm going to do, motivated by the fact that the tangent is increasing and the tangent takes the value 1 by square root 3 somewhere. I don't know if you can recall this, but the tangent of pi by 6 significantly is 1 by square root 3. And pi by 6 is also the length of each of these equal intervals because I've subdivided this interval of length pi into 6 equal pieces. So Pigeonhole takes shape. I take these 7 numbers. 2 of these numbers, which one can call x and y, go into the same box. So here is x going into this box and y also going into the same box. These go into the same box because I've created boxes between this and this in a manner such that these boxes signify a random real number to put things in. Now, here is the leap that has to be explained. What did I begin with? I began with any 7 real numbers. And to use Pigeonhole Principle, I divided a certain interval which did not cover the entire real axis into 6 equal parts. So the obvious question that one asks is, how did I choose to place my x and y within the interval minus pi by 2 and plus pi by 2? What if my numbers x and y were outside this to begin with? Because the numbers that are given to me are arbitrary real numbers. So what I really should have done is somehow thought of covering the entire real axis, all the real numbers, by just this interval. And that is exactly where the tangent function comes in for the second time. That graph will show you that the tangent function, in fact, and I will write it here, is a mapping that takes minus pi by 2 plus pi by 2 into the real numbers, or into minus infinity plus infinity. And it takes it in a manner that is both 1-to-1 and onto. So therefore, I could think of not only taking any real number between minus pi by 2 and plus pi by 2 as a real number. I mean, I could map an x there into a real number called tangent of x. But more significantly for me, I could take any real number and map it back to a point in the interval minus pi by 2 plus pi by 2. That function you could call tan inverse or whatever. But the most important thing is that there's a two-way relation between the interval minus pi by 2 plus pi by 2 and the set of all real numbers, minus infinity plus infinity. I will simply write it here. Minus pi by 2 plus pi by 2 is in correspondence, 1-to-1 correspondence with minus infinity plus infinity. So I can go back and forth via the tangent function. So in fact, what I could do to begin with is not really think of minus pi by 2 plus pi by 2 as the interval to subdivide, but really the interval minus infinity plus infinity to subdivide, so to say. So either I change my notation and don't call this minus pi by 2 plus pi by 2, or equivalently, don't think in terms of x and y, but really replace this x and y in terms of their tangent values. Because what the tangent values will then do for you is take a random real number in this interval minus pi by 2 plus pi by 2 into the real axis. The way the problem is stated right here, it is given to be any real number. So I take this real number that is given to me. I take the inverse tangent function. I take tan inverse of x, and I convert that into a point in the interval minus pi by 2 plus pi by 2. Once I convert this into a point in minus pi by 2 plus pi by 2, the pigeonhole takes over from the place I'm at. And I can conclude that these two numbers, really tan inverse of x and tan inverse of y, lie within pi by 6 of each other. So what this pigeonhole principle will therefore say is tan inverse of x, I don't want to leave this page, which is why I'm writing it like this, minus tan inverse of y is no more than pi by 6. And because I put an absolute sign, I could also put a 0 at the other end. All right, so where am I? I've got this x and y randomly given, real numbers. I have no control over how big those numbers are. I want to bring them to size. I take the tan inverse of x and the tan inverse of y. Now I'm looking at two numbers, a and b. tan inverse x and tan inverse y, that lie within this interval minus pi by 2 plus pi by 2. And by pigeonhole principle, two of these numbers have to be such that their difference is no more than pi by 6. I'm almost in shape now, because all I've got to do is recognize that the tangent of pi by 6 is 1 by square root 3, and the tangent is an increasing function. So if I look at the tangent of these three quantities, tan 0, tan of pi by 6, I get the upper and the lower bounds of 0 and 1 by square root 3. And by the trigonometric identity, which tells me what is tan of a minus b in terms of tan a and tan b. Recall that tan of a minus b is tan a minus tan b over 1 plus tan a tan b. From this trigonometric identity and the fact that it's increasing, I get tan of, maybe I need a fresh sheet. I've got tan of a minus b is tan a minus tan b over 1 plus tan a tan b. And if you use this together with the fact that I had a as tan inverse x from my previous slide and b as tan inverse y, apply this to this particular pair of numbers, you will conclude that tan of a minus b is equal to x minus y over 1 plus xy. And because tan is increasing, and the fact that you had this a minus b lying within 0 and pi by 6 will then tell you what you wanted, that 0 is less than equal to x minus y over 1 plus xy, less than equal to 1 over the square root of 3. Little tricky, unless you made the connect with trigonometry, unless you saw that pi by 6 was equal to 1 by square root 3, this would not have been this easy. So there are little bits of divine intervention, if you like. The way you connect with 6, the way you think of 6 is because there are 7 real numbers. Pigeonhole immediately lets you think of 6. And then you connect 6 with 1 by square root 3 in the sense that tan of pi by 6 is 1 by square root 3, and then you're off and running. It's not one of the easiest things that strikes you, but nevertheless. All right. Now, I'm now going to go into my next problem. I'm not sure how much time we have, but if I run out of time, because there is a cap on the number of minutes you have per lecture, I might suddenly have to only satisfy myself by giving you certain hints for this problem. All right, I chose this problem because this is a significant problem in the field of combinatorics. It's a little different from others, and it's also more important than anything else that I have done in terms of importance, in terms of the fact that this is a well-known result. I didn't want to leave this out, so if it is the case that this is the last one, then so be it. What does this say? Well, you've got p and q, these are positive integers, and you have n greater than p minus 1, q minus 1. So things have been placed directly in terms of a pigeonhole concept. In some sense, p minus 1, q minus 1 kind of places itself as the number of letter boxes. N places itself as the number of letters. How you choose those letter boxes and letters is up to you. And what you really have to prove is what comes up. You take any sequence of n integers. Now, integers are not significant. You can take real numbers, for that matter, or rational numbers. And it's also not significant whether or not they are distinct. But for the sake of definiteness, although I haven't added it out here, let me also add that the sequence of n integers are distinct. If they're not distinct, the result will still hold good. I will just have to change the definition of what is increasing and decreasing. So I've got n integers, and you have to prove that there is either an increasing subsequence of length p or a decreasing subsequence of length q. So let me hold that slide for a bit, because it will take a while for us to this whole thing to sink in, and then I will try to work out what I'm trying to prove out here. So again, p and q are positive integers. N is bigger than some quantity that involves p and q. You're given a sequence, which means you are given a set of numbers ordered in a particular manner, something that is in bijection with, that comes in a certain array, in a certain formation, in a certain. So I will end this with a significantly important problem, which goes back almost 100 years. I feel that this is probably a good place to end. I may not be able to complete the solution in all, but I will try to tell you how to set up the problem and how the pigeonhole may be applied, and I hope that you can work this through. So you have two positive integers p and q. You have n bigger than p minus 1 into q minus 1, and you have a sequence of n integers. Now these integers need not be distinct. So these integers are listed in a certain order. That's what a sequence means. Let's say a1 to an. And what you have to prove is that this sequence will contain a subsequence. That means you can take, if you like, some of these terms but not all, but take them in the same order in which they appeared in the original sequence. Now this subsequence will have either the property that they're increasing, that means each term is bigger or equal to than the previous one, and there are p such terms, or it is decreasing and has q such terms. This is what you're required to prove. Now, since I'm running out of time, I'm going to hurry a little bit. So what I have is n terms, a1, a2, a3, and so on and so forth, an. I'm given that n is more than p minus 1 into q minus 1. Now this particularly suggests that I somehow have to make up a box consisting of p minus 1 into q minus 1 slots, or p minus 1 into q minus 1 letter boxes. I have to place n letters in them. And the moment I place n letters in these p minus 1, q minus 1 letter boxes, two of these letter boxes will have the same property, whatever the property is. Now, how do I set this up? So you fix a symbol I. For simplicity, I'm going to just start with 1, a1. You can do this for any I. And you attach with it a pair of numbers, which are positive integers. For 1, I will call this L1 plus and L1 minus. What does L1 plus and L1 minus mean? So all right, so I have the sequence. Let me plot it on the y-axis, because then you can think of going up and down more easily. Let's say this is my A1. Let's say my A2 is here. Let's say my A3 is here. Let's say my A4 is here. And let's say my A5 is here. And I'll satisfy myself by just taking a small example of n equal to 5. What does L1 plus mean? It means that you start at A1, or at the first slot, and you look at the subsequence starting with 1, and look at the largest or the longest subsequence that you can find, that's a plus, together with increasing. So the plus actually denotes the increasing part. So the L1 will denote the longest subsequence you can get starting with A1. So therefore, in this particular instance, it could be something like A1 followed by A2, followed by A4, followed by A5. So L1 plus would actually be 4, because there are 4 terms in the sequence. L1 minus would be the length of the longest subsequence that is decreasing. So in this case, starting with A1, you can go A1, A3, and L1 with a minus would then be 2. In a similar manner, you can construct pairs of positive integers corresponding to each AI. Now, assuming that the result of this particular problem was not correct, the conclusion was supposed to be that you either had one of these LIs, pluses, this is what you wanted. You wanted an Li plus to be greater than or equal to P for some I, or you wanted an Lj minus to be greater than or equal to Q for some j. Assuming this is not correct, you would conclude that all the Li pluses and all the Lj minuses are between 1 and P minus 1. If that was the case, then the number of choices you would have for these pairs, so you're looking at pairs Li plus, Li minus, such that I and j lie between 1 and n. The number of pairs here, sorry for writing all over the place, will be no more than P minus 1 into Q minus 1. Now, if that is the case, then you have a problem. The pigeonhole comes in, n is more than that, and you conclude from the pigeonhole principle that there will be two numbers, two distinct numbers I and j, for which you will have, let me turn the page and conclude right there, you will have the situation where Li plus, Li minus, the ordered pair will equal an Lj plus and an Lj minus for some I not equal to j. Now, since I've run out of time, I would like to conclude right here and leave this as an exercise to prove that this particular situation cannot arise. Plainly put, if you have two different points, ai and aj, and both of them have the same longest subsequence, there is a problem. The same thing would arise, the same contradiction would arise if you look at the longest decreasing subsequence. With that, I will end my set of problems and my second lecture for the pigeonhole principle. I hope you take this as an opportunity to verify and work on other problems on the pigeonhole principle. Thank you.